Hello, good evening, and welcome everybody to the Sigma meeting for September 2022. We're back on Zoom again, as you can see. Reason being is that our speaker tonight is over in Paris, so it's a bit of a long trip to get him into Lambride. Okay, so first of all, I want to start off by welcoming everybody to the meeting, not just Sigma members, but also any visiting members we have from HAS, from Aberdeen, and from Caithness. And of course, a very special welcome to any first-time visitors we have today. You're more than welcome. Hope you enjoy the meeting, and hopefully you'll become a member of Sigma very soon in the future. Okay, just before I start, I want to mention the BAA autumn meeting that's happening next week at the university in Elgin. So it's open to everybody. I know we've got about 50 people bought tickets already, which is fantastic, but a few more would always be good. And to say, tickets can be purchased. It starts next Friday evening. The doors open at 6:30, I believe it is, and for us, or 7 o'clock, 7:30 start. It's all on the website anyway. And I say tickets can be purchased from the BAE website, which is baa.org, or you can get a link for that from the Sigma webpage, with sigma-astro.co.uk. Okay. So as I say, tonight we're actually back on Zoom because our speaker, Michael Peterson, was hoping to be coming up to see us, but he's been waylaid in Paris of all places. It's terrible, eh? But he was telling me tonight that Paris is actually shut down at the moment, or just coming back to work. They seem to have August off, which is wonderful. I think I'm as if I can sort that out with my boss and do the same thing sometime. Okay, so I would just go through how the meeting works for those of you who've not been to a Sigma meeting before. Basically, we start off, say, with the main talk. We will have a little 10-minute break. It gives us a chance to get away from the screens for 10 minutes and do anything we need to do. Gives you a bit of comfort break. We'll then be back in the second half, and so it's only a 10-minute break. We're back in the second half. Stuart's going to be doing his final space news of this year. We've decided that space news will be split. He'll do them in the summer, and Mick would be doing the More Sky at Night, more so in the winter, or autumn, winter, and spring months. Okay, so Mick will be coming in as well to do the first More Sky at Night of the year, of the season, of the year, as he did do them earlier on. And then I'll do a little bit of club news, and we look at finishing around about 9:30-ish, something like that. So on to the main topic for tonight, which is a talk from Michael Peterson. Mike recently accepted a Stephen Hawking Fellowship at the University of Edinburgh, and is a member of both the Institute of Astronomy and the Higgs Centre for Theoretical Physics. He is currently finishing up a research year at the Institute of Astronomy in Paris. He grew up in the north of the United States, in Minnesota, and did his PhD in the northern United States at the University of Massachusetts. Mike is also an avid cyclist. And so, do you take part in the Tour de France? No? Yes,
Oh, absolutely.
And he's also an avid cook as well, believe it or not, when he's not thinking what's happening in the universe. So what I want to do is hand over to Mike, and we'll get this started. And Mike, thank you very much for coming along. And we will get you to Moray one day, and we'll take you for a whiskey and a wee dram. But for now, over to you for your talk for tonight.
Well, that sounds fantastic to me. Thank you. Thank you so much for that, for the very kind introduction. And I'm very happy to be here to get a chance to speak to you tonight. I do wish that I was able to be there in person, but unfortunately, owing to COVID delays, my year was pushed back just slightly in Paris. So I'll be back in Edinburgh hopefully before I know it. So in about a month's time, actually. So I was in Edinburgh actually for 2 years before doing a postdoc. It's a pretty standard track to move around while you're doing a PhD. So as you can hear, I grew up in the United States and then moved to Scotland for a postdoc after I finished my PhD, and really fell in love with it. And so I'm excited to get back there after really warming up some more of my research here this year in Paris, that is. So the talk tonight is called A Billion Years of Stargazing. And it has to do with both sort of what we see when we look up at the sky at night, connections I think that we can all make with the night sky. And then it sort of progresses. We have to go back about 1 billion years to reach the point where my research really starts to interface with the type of things that you see in the sky. And so that's where we're going to end up going over the course of the talk. So I did structure the slides here so that if you put me and my little inset down in your lower right corner, you should be safe from blocking any of the slides, I think, during the talk. So hopefully. So again, this is a nice photo that that I took, and also really I got into astronomy and sort of what one might call the traditional way of looking up at the sky at night as a kid and being enthralled by what we saw. And so this is a shot from a trip that I took once to Arizona to Kitt Peak National Observatory, where I did some work during my PhD and had a chance to. Once you get the telescope set up and taking pictures of its own, you can run out and take pictures with your camera. And so doing some work with this. And of course, as I probably don't need to tell anyone here, there's plenty of constellations in the sky, plenty of old friends to look at here. Some favorites here, maybe some less favorites or some less known ones. So of course, across the sky, you've got Orion, which we'll be focusing on a little bit in the context of this talk and how Orion looks over the course of some historical time. And you've got sort of Eridanus, the long snake one here, and you've got Cetus, sort of the sea monster, and you've got some of the funnier ones, like some of the later named ones like Fornax and Sculptor over here as well. And then some of the old ones from the early writings of prehistory, even. So Canis Major, of course, and then Lepus here, the hare, which both appeared in Ptolemy's descriptions, which will come up later. And I like to, when I look at the night sky, I always think about how it seems so static and unchanging. You know, from year to year, you see the same things in the sky. There's a little bit of modulation, of course. You see summer constellations and you see winter constellations. And I personally, of course, am always thrilled to see the sort of change that takes place over the course of the year. But I know even over that 6-month time span where the stars are going to appear when they come back, when we get to that right time of the year. To orient you over the course of the talk here, we're going to think about time looking into the past. So I'm going to talk through this arrow of time that's actually running backwards. So this is the time that we're looking back. And I'm doing this in kind of a funny spacing here, because as you'll learn over the course of the talk, time in astronomy gets very long, very quickly. So thinking about, going from a year ago to sort of 10 years ago to 100 years ago to 1,000 years ago, and then we're going to transition into scientific notation. Here's what I want you to focus on: the number. So there's 10, and then there's superscript 4, and then 4 is telling us how many zeros are after the 1. Okay, so as we keep going, we go from 10,000 to 100,000, 10 to the 5 here. We get to 1 million out at 10 to the 6. So that's sort of where you want to think about, okay, what did the sky look like 1 million years ago? To 10 million years, to 100 million years. And then finally, we're going to target this 10 to the 9, this billion years. What does the sky look like over 1 billion years? If I was a stargazer over this course of this billion years, what would I have seen change in the sky? And that's sort of the premise of this talk, this question of, okay, this sky that I was talking about, how I fell in love with this view and really know all of the constellations and know where everything is in the sky. What is it really unchanging? If I come out here and look at all of this time through cosmic history, even though it seems completely unchanging to you and I, is that actually true? Of course, I probably wouldn't be giving you this talk if it turned out that over 1 billion years, you saw exactly the same thing over time. So now the question sort of pivots a little bit more towards what actually changes and how do we know that it's changing? How do astronomers measure this? What are we actually studying to try and get to make some precision measurements of the changes? Okay, so coming back to this view of the constellations, you sort of know already because of observations that things change over a little bit of time. And your first hint, actually on the smallest timescales, is that you see variations that make eclipses. So you can think, okay, an eclipse maybe comes up every couple of years. Partial eclipse, a solar eclipse, is even a little bit more rare. Okay, something must actually be changing. And there's planetary conjunctions, and there's and then there will be comets and meteor showers. Okay, So something's changing on a different time scale here. Then that's sort of roughly on the 10-year time scale. So you're looking and you think, okay, well, 10 years ago, the planets were sort of in a slightly different location. They were all in different conjunctions. There was a great eclipse a couple of years ago, but there won't be another great eclipse for a long time. And that's on this 10-year time scale. On the 100-year time scale, it's a little bit more cynical in the sense that, okay, one of the things that's unavoidable when you look at the image from before is that you see quite a bit of light pollution that's changing our relationship with the night sky. As an astronomer, that's something that I'm very passionate about, but it's not going to be the main topic of this talk. But this is just to acknowledge that the sky is changing over time, and this light pollution is actually a big contribution to how we experience the sky presently. Okay, but now let's talk about, let's keep going back in time. So these are probably things that you've heard about before, variations that you at least have heard or maybe understood in some way. You know when eclipses are happening. And so now we've pivoted. We're still on Kitt Peak. This is one of the large telescopes down here at the bottom, the 4-meter telescope. So you can see how far away I'm actually standing from this right now. But this is to take a large sky image, and you've got some favorite asterisms. I'll be very careful, not actually constellations here, the Little Dipper and the Big Dipper. And you probably know something that's unique about these and why we would focus on them. And that's illustrated during this video, okay, that I'm about to play. What's going to happen? You sort of know, okay, so let's start the video. Stars start to wheel around. There was the old location of the dippers. Here we go over the course of the night. So this is a variation on a night scale. We all sort of know what's going on there. And if I cheat a little bit and tell you zoom forward in time, what is it actually going to look like? Okay, so this is if you stacked all of those together, you can make star trails. And you notice something unique, of course, which is that they make these big concentric circles sort of around this one brightish point. You probably know what star this is. Of course, this is Polaris. So we're looking essentially directly north in this image, and you're rotating around it. Okay, so that's variation that you're comfortable with. But it turns out if you waited long enough on this 10,000-year time scale, the Earth's axis will tilt in the opposite direction. Okay, what does that mean? You've probably seen this diagram before. This is why Polaris, the North Star, that star that was at the center of the circle before, has this unique property that as you move in latitude, the height of Polaris above the horizon actually changes, and that's due to this tilt. Or it's tilted by 23.5 degrees. This is what ends up causing quite a bit of this change over time. And what's going to happen in 10,000 years is that actually this 23 degrees will be tilted the exact opposite way. So there's this cyclical pattern where 26,000, to be precise, 26,000 years from now, the Earth's axis will be tilted in the same location. But 13,000 years from now, it will be exactly opposite to this. And this has a profound effect on what you would observe in the sky. If we were observers, even just on this, I'm saying even because I'm an astronomer, even just on the 10,000-year time scale, you would see a completely different sky. What does that completely different sky look like? Okay, let's bring this back. It would look like these concentric circles if we could make this time-lapse image, except over 10,000 years, you'd start to see all these circles trace out spirals. And Polaris would no longer be at the center. They would all be orbiting different, they would all be circling, not orbiting, they would all be circling different positions on the sky. So if we came back in 13,000 years, Polaris wouldn't be at the center of this circle. Polaris would be doing its own circle around a different point. And that's just on the 10,000 years. So that's actually relatively short, as astronomers think, of course. And I'm going to argue that these are all what I'm going to call put under the umbrella of solar system timescales, anywhere from 1 year, us going around the sun, to 10,000 years or 20,000 years, Earth's axis tilting in the opposite direction. That's solar system timescales. So I consider those to be relatively short. Those are things that we've probably all become familiar with. You're probably even familiar with Earth's axis tilt if you've used precision coordinates to look up galaxies or look up locations of stars. You'll know that those are reported sort of every 50 years. We're inching ever closer to getting a new coordinate system, abandoning or leaving behind the J2000 coordinate system and moving to 2050 in the near future, of course. Okay, so again, we're heading towards a billion years. In this next time scale, the 10 to the 5 up to 10 to the 8, these are what I'm going to call galactic timescales, and that will have its own set of variations that we'll explore here in a minute. And then even longer at 10 to the 9 or 10 to the 10, which is where you're talking about 10 billion years, the age of the universe-ish. I'm going to call those universe timescales. And so that's what we're building towards. We're going to go through galactic timescales next, see what changed on the sky, and we'll finally get to the thing that I'm really interested in, the universe timescales. Now, of course, I'm cheating a little bit here in the sense that I titled this talk "A Billion Years of Stargazing," as though humans have been around for a billion years and had plenty of time to look at this. So let me give you a little bit of benchmarks, or a few benchmarks here, for what's going on as we look at these different timescales. Okay, of course, Earth forms about 4 billion years ago, so we'll put that sort of in the middle here. So this is, in theory, the earliest that you would ever observe from Earth. But even beyond that, let's say you wanted to observe from Scotland. Scotland and England finally docked about 400 million years ago. So you're somewhere here between 10 to the 8 and 10 to the 9 that you would actually be able to observe from something that looks like what we now know today as Scotland. Coming in a little bit further, of course, then it takes quite a bit longer for dinosaurs to be roaming the Earth. So we're talking about in the tens of millions here. So you know that dinosaurs are wiped out at 65 million years ago. So sort of between 65 and 200, you're seeing dinosaurs roaming the Earth here. Earliest humans, so the earliest that this would ever actually make sense for us to say, oh, I'm a real human observer of the sky, and we could imagine some of our earliest ancestors probably doing this. It's about 1 million years ago. So you can see that humans have actually observed many, many, many cycles of this Earth tilting on its axis, this 10 to the 4 scale. There's a factor of 100, of course, between 10 to the 4 and 10 to the 6. So there have been at least 100 of these variations of Earth's axis tilting, 100 times that Polaris has been the North Star and not been the North Star and come back. Okay, but recorded history, much shorter than that, even shorter than a single period of Polaris orbiting its location. But that isn't to say that people haven't looked at the sky for a long time. Of course, Ptolemy, as I mentioned at the very beginning, was already writing locations of constellations that we know 2,000 years ago. All right, let's move to the galactic timescales now. So moving to these galactic timescales, we're now looking at the sort of 100,000 year timescale. We're thinking about 100,000, 10 to the 5, or up to the million timescale. And that's going to necessitate us taking a whole picture of our galaxy. You've probably seen this image before. This comes from the European Space Agency's Gaia satellite, of which Edinburgh is a key member. The University of Edinburgh writes a lot of the data reduction that goes into making these beautiful images and bringing the beautiful data from Gaia to life. And we're going to use a lot of this data throughout the talk. This is a big piece of my research, is using data from this satellite. There have been some truly fantastic results that have come out of this. Gaia is still observing right now, actually. It's we're hoping, big fingers crossed, that it's less than 2/3 of the way, maybe halfway through its mission to measure the motion of all of these stars in the sky. We'll talk about what that means in a minute. But for now, let's focus on just how this view of the Milky Way galaxy is taken from Gaia. But this is unwrapping the whole sphere of the sky. So this is pretending like Earth's not in the way. You can see all of the sky at once. If you could be everywhere on Earth at once and it was always night, this is what you would see if you unwrapped the globe onto the sky. Okay, so hopefully you've seen something like this before, and you've seen this. The center of this image is the galactic center. So we're looking directly at the galactic center. And the opposite sides, the ends of the image are looking away from the galactic center. I find it a little bit hard to think like that, so I'm going to help us and think about something that looks sort of like the Milky Way. We can't take this type of image, of the Milky Way ourselves, but we can find galaxies that we think look very similar to the Milky Way. This is a picture from Hubble, taken of this galaxy with the sort of sparse name NGC 5754, but this is a great galaxy to try and compare to our Milky Way. Okay, so in this image, what you're seeing, if you're comparing to this unwrapped image in the background, is that you're seeing us looking at this location. We're here. And we're looking towards the galactic center of that image. And then you're looking at a big circle that's unwrapped on the sky. So the edges of that image would be looking directly away from the galactic center. Now, I drew this little tiny circle here because this is about where the sun is. So our Milky Way galaxy has this bar through the middle, which was a big part of my thesis topic that I'd be happy to give other talks about. We're not going to focus on that today. And there's spiral arms here, of course, and the sun is located, we think, somewhere in one of these sort of more outer spiral arms in this. And the circle that I drew here is roughly the size scale on which you see all of the constellations in the sky. So we're getting to a much larger scale now. All of the stars that you see that make up constellations that we see from Earth, they would all fit inside of this little circle. As a matter of fact, the thing that you see, of course, that's the furthest away when you look at images of the sky, is going to be actually that Milky Way in the backdrop, that band that was across some of the previous images. So you can imagine that this is a little surprising. This is not very far. And I'm going to make a little bit of an analogy here that will make more sense in a minute. And say that this is, you can think of this sort of as let's think of this as the size scale of a train car. Okay, and a train car, actually, the analogy makes a little bit more sense because you think, okay, I'm riding in the train, and inside my car, for the most part, people aren't moving. Everyone's kind of sitting in fixed locations. And that's sort of what I think of as the constellations. But if you came back and looked at this over time, people might have switched seats. People might have gone to get a tea or something, or gone to the restroom. The configuration has changed a little bit. And this is all what's happening just inside our little train car, not any distance really in the grand scheme of things here. So that's what I'm trying to say, is that inside of our train car are all of these constellations. And let's just focus on one and start to see what happens as we extend our time scale. So I showed you a video before that was looking at the sky over the course of a night, and then talking about what happens over 10,000 years. But let's zoom way forward in time and ask what happens over 1 million years. Now, there's something to know about this, of course, which is that the Gaia satellite, which took all the data for this, is focused on measuring the precision motion of all of these stars. Every star that you see in this image, Gaia is actually able to measure how it will move over the next million-ish years. So even though there are these teeny tiny distances that they've moved over the past 5 years that Gaia has been observing, the technology is so exquisite that it's able to detect the tiny little motions in these. Okay, so here's Orion. We've known this, we've seen this before. I've drawn the lines here, and you know Aldebaran is in Taurus, so the next constellation over. Let's just ask what happens when you run Orion forward for 1 million years. And keep in mind, these are real measurements. This is a real thing that's going to happen looking forward, but you can imagine what would happen if we ran backwards in time. Okay, so here we go. So the stars immediately start to move very quickly. And if you pause it sort of right about here before we start going in reverse, Orion isn't visible in this image anymore. You can see some parts because we know what Orion is. But if you're an ancient observer 1 million years ago and you look up at the sky at this, you don't pick out the constellation Orion. Maybe you pick out something that looks a little bit more triangular. You pick out these 3, or you actually include Aldebaran, and now you have a sort of parallelogram style thing. But on this sort of time scale, Orion doesn't look anything like what we think it looks like now. You can also notice that the Pleiades has blown into this image as well over the course of this. The Betelgeuse has taken way off and is no longer part of this. So now we can run back over the 1 million years and bring ourselves back to the sky. I'll play the whole video again. So this is running forward 1 million years, and then it will run back 1 million years as well to bring them all back to their locations that we know and love in the sky. So this is what evolution in the sky looks like, or the change in the sky looks like over 1 million years. And that's now getting us towards really the meat of the galactic timescales here at this 10 to the 6 being 1 million years. Okay, and at that time scale, the constellations that we know, that we see in the sky, are completely unrecognizable. If you were to start from scratch, you would pick completely different constellations in the sky. So this idea of the unchanging sky we've already been able to make these precision measurements and show, wow, the sky is completely changed on this sort of time scale. And we still have at least 3 rungs to go before we get to the billion-year time scale. All right, so what's next? If we start to think about things on the million-year time scale, what happens if we push to a slightly longer time scale from there? So the next time scale up, as you may have already ascertained from looking at that image, things in astronomy love to move on orbits. So here we're orbiting around the center of the Milky Way. The sun follows roughly this galactic orbit. Now, galactic orbits are actually very long. So if we're thinking about timescales here, and we're following our train analogy, following our train around this track, this takes about 250 million years. So we're talking about, if we go back to our time scale here, this is 1 million, this is 10 million. So the time scale for orbiting is already out at this 10 to the 8 time scale. So we've really zoomed ahead here a little bit. But that is to say that actually, if you just consider part of this, so 100 million years roughly from now, we'll be on the other side of the galaxy. 50 million years from now will be sort of 90 degrees around, or sort of a quarter of the clock face around. Our train will have completed roughly a quarter of its journey. And so the analogy here that I'm trying to make with the train is that we saw the constellations are what's happening inside of our train car, but the train's actually moving across the countryside here, or around the galaxy. And so what you're seeing out the window is really starting to change over time. Okay, so what can we do about that? Well, it's a little bit harder to measure what's happening, but we know that this image from Gaia is roughly what it looks like when we look out the window of our train car. And this circle that I'm drawing here is more or less the volume that you can see, with some notable exceptions that I'll make in a minute. But this is more or less the volume that you're seeing when we look at this Gaia image. And again, now that we have this all up in one place, I just want to remind you that we're sitting here in the train car. If you look towards the galactic center, that's just like looking at the center of this image. And if you look away from the galactic center, so out the left side of the train here, then you're looking at the edges of this image. Okay, so that's what Gaia is seeing roughly spaced out over the sky. And I'm again going to caveat this and call this the near field. So you have to imagine on the train journey that you're actually looking at something that's not that far out the windows of the train, maybe the 2 fields on either side of the train or something. We haven't even started to look at the distance yet. And on the near field, you're going to start to see differences. You could imagine that these dust clouds that are in front of the stars, so all of the dark regions here are dust clouds. All of these dust clouds are going to appear to move as we start to orbit around the galaxy. You can also wait and ask the Gaia satellite, what are all of the stars in this image doing? And what you start to see is this crazy cross pattern of stars that are just absolutely crisscrossing the sky. So we're riding along in our train, and this is roughly what we're seeing. We're seeing all of these stars moving, distant stars moving, close stars moving, and the sky is just changing very rapidly if we're thinking about things on the sort of 10 million or 50 million sort of year time scale. And if you wait very patiently, actually, for a little while, so this is sort of immediately after you've started your train journey, everything starts to be scrambled. If you wait very patiently and start to look for patterns in this, you'll start to see that actually all of these arrows, if you brought them all together, would have sort of a common path. And that's this is what this image is. So the Gaia team has put together this great data analysis that took the image from before, this really spaghetti image, and asked, okay, what's actually happening on average across the sky? And this is where you start to get the sense of how we're traveling around the galaxy and how we know that we're actually traveling in an orbit. And the analogy that you should think of here is that this is very similar to the train going through a rainstorm. So we're in a train, and you know that rain falls straight down. But of course, because you're in the train, it looks like the rain is coming towards us, or it looks like the rain is streaking down the windows diagonally. And that's effectively what you're seeing. So we know that we're traveling sort of in this direction because all of the arrows are pointing outwards from that. Very similar to like you would see if you were riding along in a car or in the train, and raindrops were hitting your windshield or running down the window. So this is the average from the Gaia satellite. And I just find this type of image to be absolutely amazing. The fact that we're able to look out at this distance almost to the galactic center, all of these stars, it's literal billions of stars that Gaia is measuring this for. And you take these billions of stars and you want to learn something about how we're actually moving across the sky. And this is where you start to see, oh, we can actually see how we're moving around the galaxy on that 250 million year time scale. But our instruments are so powerful that we can see this type of motion even just on the simple 5-year time scale. Okay, so this is what we're seeing. We think as we take our average measurement, this is on the medium time scale. And so after 10 million years or so, you think about that spaghetti image, that Gaia image, the one that we saw of the beautiful galactic center and the dust clouds, that image will be completely unrecognizable. If we were observing 10 million years in the past, you wouldn't see anything that looks like that. You would see completely different dust clouds. You would still have a galactic center, but the viewing angle that you would be seeing it at would be completely different. We would see the bar of the galaxy at a different angle. That entire image would not look anything like it does. All right, so that's the 10 million time scale. In order to get up to the real galactic time scale at 10 to the 8, we have to take one more step back. And so now we're really looking a long ways out of the train windows here. And so the image that I showed you on the previous slide, part of the Milky Way galaxy, this is a schematic now, not a real image. We can't take anything like this, but we can put together some very nice schematics. Everything I was showing you before fits well within the disk here. So here's, let's imagine this is our spiral arm that we were at. The Earth is doing this very small, the Earth and the Sun are doing this very small orbit around the center of the galaxy. But if you look even further out, there are other galaxies that are doing their own orbits, and they're fixed in the sky in positions right now, or so they seem, because this is where we measure them all at the present day. But you know over time that they weren't there, and we on Earth and this orbiting the sun were not at our location in the galaxy. So how do these things change over time? All right, so now we're back to our train. We're looking very far out the window. And this is sort of where you start to see some real power of the Gaia satellite. So the Gaia satellite, not only does it measure all of the stars in that volume that I showed you, 1 billion stars or so, but it actually is able to see these collections of stars that are even further away. So Gaia is able to pick out individual stars in each one of these little dwarf galaxies and globular clusters. So each one of these dwarf galaxies, Gaia is precise enough to measure how they're moving. And so if we pretended that we only actually had eyes for these really distant things, we don't care about the near field stars, maybe they're blurry to us and we're focused on just the far field things in the distance. And that's what is being circled here in this image. So again, this is the all sky image. I've grayed it out so that you can see, so that you can really focus on what's happening in the distance. And everything that's circled in blue is a globular cluster, those images that you've probably seen of 1 million stars in a dense knot. Or the things that are circled in red are dwarf galaxies, which are just miniature versions of our own galaxy, of something that looks like our own galaxy. And I look at this image and I think, oh, this is great. We can make our own constellations from this now. So let's pretend that we are really wanting to make our own constellations. This is purely pretend, of course, here right now. Here's our constellations. How are these going to look? These are dwarf galaxies and globular clusters that I'm very familiar with. There's only a few of them, so we study them very seriously. What are we actually going to see in here? Of course, let's take our imagination to the next step. And I always think that looking at constellations is a little bit Picasso-like. So here, well, let's borrow a little bit of help from Picasso line drawings here to bring these to life. Maybe this one's a dove, this one's a squirrel on its side looking up, and this one's that dachshund that he drew. Maybe this one down here is the owl. But what we know is even if we pretended that these constellations were real, which again, they're not, although if you wanted to come up with globular cluster or dwarf galaxy constellations as a group, I would completely support that. But you can still recognize obvious patterns in the sky just looking at these, and I just connected some of the dots. But Gaia, of course, is going to go and spoil all the fun. And if you were to ask, what does it look like 100 million years ago? Gaia is able to measure where those would have been 100 million years ago and how they're going to move. So this is Gaia measuring their motion into the future. But you can imagine that this is how they would have moved in reverse. And of course, if you take these now, and you look at the globular clusters are moving quite a bit. At the center, there's a lot going on, of course. So these constellations that we just drew would be very warped. And you have this, really stretched out owl, and the dachshund's really stretched out now. And maybe the squirrel looks a little funny. So these constellations would have really warped over time, owing to the motions that we had of these globular clusters and dwarf galaxies. But again, these are completely static and unchanging to us as observers, because the time scale that we're considering here for these to warp is about 10 to the 8 or 100 million years. All right, so at 100 million years ago, if you were an observer 100 million years ago, Scotland has already formed, so we can actually be real Scottish observers. The galaxy locations are completely unrecognizable. You would not be able to, if I went back in time and told people where to look for galaxies, there would be nothing there. They would be in a completely different location, in addition to us having completed most of our loop around the galactic center over that time scale. All right, so at this point, we've really reached the end of the galactic time scale. This is 100 million years. That's the time that it takes us to orbit around the galaxy, or so. 250 million is a galactic year. Once you get up to 1 billion years, you're already talking about universal time scales, going around the sun, going around the galaxy 4 times. Okay, so we've gone around the galaxy 4 times. We're back to where we started. The sky looks like this 1 billion years ago, except I've made one key change. And this is a very important part of my research. So if you've seen this image too many times, like I have, this one will look a little funny because I've subtracted something from it. So I'll give you a second to think about it, take a look at this and imagine what would be different. We're at the same location in the galaxy, but something's different about this image. Okay, something's missing is the hint. 2 things are missing, actually, would be the even larger hint. And what you're seeing on these universal timescales is that the night sky has actually undergone a huge change, because if you got it right, congratulations, the Large Magellanic Cloud in the southern hemisphere that you've been seeing this whole talk, but I've been purposely not talking about, actually isn't visible 1 billion years ago. So even though you're at the same location in the galaxy, this large dwarf galaxy that's very nearby to us now, very near, of course, being 50 kiloparsecs, which is going to be 150 light years away. So you were thinking it was very close, but it's of course not. But 1 billion years ago, the LMC started over here on the sky, but of course it was significantly further away, 5 times further away. So you actually wouldn't be able to see it. But this is going to be a very precise schematic of what would have happened 1 billion years ago. So 1 billion years ago, there would have been a really faint Large Magellanic Cloud quite a long way away. You wouldn't have been able to see it. But as time runs forward, you would start to see this sweep across. So we just ran through 1 billion years of time. I'll play that again. What's going to happen is that you're going to see the Large Magellanic Cloud sweep across the sky. And that was just running through 1 billion years of time. So what happens? The Large Magellanic Cloud starts to be visible, and it sweeps into its current location today. We're able to measure this again with the Gaia satellite. This is not to ignore the Small Magellanic Cloud, which is a companion that fell in at the same time. But these would have been conspicuously absent from the southern sky 100 million years ago. So again, here's the image of the all sky. I wasn't talking about these before, but 1 billion years ago, you wouldn't have been able to see the Large or Small Magellanic Cloud. Why is this important to me? This is a big part of my current research actually right now. A couple of years ago in Nature and Astronomy, Jorge Penarrubia, who's a professor at the University of Edinburgh, and I wrote a paper where we used the Gaia satellite to measure the motion of the Large Magellanic Cloud, and crucially, the motion of our galaxy, the Milky Way, in response to the Large Magellanic Cloud. So in just a couple words, because I'm running out of time here, but I'll wrap up quickly. The whole galaxy here, the whole Milky Way is actively traveling in one direction, was what we found. So the Gaia satellite indicates that while we're orbiting the galaxy, and if you remember the image of the averaged spaghetti, we were traveling sort of in this upper region. But what Jorge and I found is that there's actually a small deviation where we're actually being pulled. Yes, we are being pulled strongly in this upwards direction, but there's actually a little bit of excess pull to the lower direction. Now, we made sense of this because you can think of the Milky Way as a big ship, and it takes a very long time to turn a boat. So the Large Magellanic Cloud started in this location, the very precise schematic that I showed you before, and the Milky Way started heading in that direction. And then the Large Magellanic Cloud swept across the sky to where we see it today, but the Milky Way hasn't yet had time to catch up. So the Milky Way is this big boat that's still headed in this old direction. The whole galaxy is actively traveling this way. It might also help to think about this in that 3D schematic. So now we're going back to that image of the Milky Way and all of its dwarf galaxies. I've struck out everything else because we don't need to worry about those. They don't pull on us. But the Large Magellanic Cloud is about the 10th of the mass of the Milky Way. So it's quite massive for a dwarf galaxy orbiting us. And that's enough to pull the whole galaxy in a particular direction. So the Large Magellanic Cloud, while it was sweeping across the sky, was actively pulling the Milky Way toward it. And that's yet another thing that's going to change how the sky appears to us, although it's much harder to make predictions for what the sky would have looked like a billion years ago because of all the other things that were changing. But in the end, what you can say about this is that actually the biggest change to that Gaia image over the course of a billion years would be the inclusion of the Large Magellanic Cloud. And so to me, that's really the story of, I'm going to go back, sorry, to me, that's really the story of a billion years of stargazing. You've got this image that probably looks a little funny to you now, that you know where the Large Magellanic Cloud should be. And of course, you can see my subpar Photoshop stitching skills here, taking it out. But this is where the Large Magellanic Cloud should be. The sky, to me, of course, as somebody who's really interested in the Large Magellanic Cloud, just doesn't look the same without these companion galaxies. And I think that's going to be the biggest change over the last billion years. So I think that we live at a great time now, as opposed to a billion years in the past, in addition to Earth not being a lava world and there being real life sustaining, and Scotland having the gorgeous highlands and islands that it has that placed 100 million years ago, that came into place 100 million years ago. We're at a great time to be observing the sky. A billion years ago, it wouldn't have been anywhere near as exciting, of course, because we're missing this fantastic Large Magellanic Cloud. So just to wrap up here, a billion years ago, Large Magellanic Cloud is not visible. That's on the universal timescales. And of course, I did put 10 to the 10 on there, the age of the universe. I'm going to stop at a billion because that's what I really care about. But you can zoom out even further. That image that I showed you of the Milky Way and its galaxies is way down here in the local group. And then if you start to really zoom out, you start to see that there's clusters of galaxies. Each one of these points is a galaxy. We're talking about a huge scale here. But if you had eyes for galaxies, you would start to see these would change on that 10 to the 10 time scale, of course. Over the age of the universe, these galaxies have formed. They've all fallen into different locations. They've all gotten to their configuration today. So 10 billion years ago, of course, the sky looks completely different because all of the galaxies are still actively forming. But that's another talk. We'll save that for another time. I can talk about galaxy clusters in other opportunities. All right, so here is just the summary slide. We talked through all of these things, the time in the past, all of the variations and what we would see if we looked at the sky and we observed the sky over a billion years. We're fairly comfortable with the solar system timescales. You know about eclipses, you know about light pollution, of course. You've probably seen Earth's axis tilting in the opposite direction. But when you get to larger scales, galactic time scales, suddenly things that we use as our favorite signposts in the sky, well, I say suddenly, but suddenly in astronomical time, constellations are unrecognizable. That very famous Gaia image of the beautiful sky, including the Large Magellanic Cloud, that image is unrecognizable at 10 to the 7 years ago, or 10 million years ago. At 100 million years ago, the locations of the nearby galaxies that you see in the sky, the dwarf galaxies, the globular clusters that maybe you've observed, those are unrecognizable on that time scale. And then at 1 billion years, near and dear to my heart because of my research, the Large Magellanic Cloud, a super arresting sight in the southern hemisphere, is not visible. And beyond that, even bigger changes. So with that, I'll stop there. That was me taking you through 1 billion years of stargazing, and I'd be very happy to answer any questions that you might have. Thanks so much.
Thank you very much, Mike. That was absolutely fantastic. I guarantee there's a virtual rain of applause going on at the moment. Just one thing I got to sort of pick up on you, though. You said rain comes straight down. Well, as you know yourself, here in Scotland, it's not really called rain until the wind is blowing at a 45-degree angle, you know. But
that's right. That's going to make our observations even harder. But you're absolutely right.
Yeah, let's say we've got no questions coming yet, but if anyone wants to put any questions in, there's a Q&A. I meant to say before we start, there's a Q&A button in your toolbar. Just click that and put a question in from Mike, and then Chris will pick them up and ask them over. Just
well, Pete, we do have some questions from Rich actually that came through on the chat.
I was just going to ask one myself. Well, not a question, but I know when I do talks and I talk about like the Andromeda galaxies coming towards us, people get very, very confused. Can you explain how galaxies can be coming towards us when the universe is expanding? This is what people seem to get very confused when I'm giving any talks with them.
Yes. So I think, again, this is the thing where you might consider the type of train analogy, right? Which is that, except now the train is much bigger. So the universe is expanding by and large, but some things are so close to us that the little random motions make it look like they're coming towards us. So it's the same way that you're in a train and you're traveling across the whole countryside, but somebody in the train could still be coming towards you, even though you know that you're both moving a long ways away at the same time. So it's all this local perspective.
Yes.
And the hard thing to get your head around is that Andromeda is actually close in the scheme of things.
And it's the gravitational pull as well, isn't it? So
that's
you're
right.
in the local group. Yeah, it's just when I'm doing a talk, people go, well, hang on a minute, we're all expanding. How can this be happening? You know.
Absolutely.
Okay, so we've got a couple of questions. I'll hand over to Chris, who will ask them over to you.
Yeah, thanks, Mike. That was fascinating, and yet again another talk that completely blows my mind when it comes to discussing scales and just the sheer size of the universe and all associated with it. Right, so Rich definitely gets the prize for being the most enthusiastic. So we got 4 questions because of a Zoom issue. He had to put them in the chat, but hopefully if we can get rid of those 4, then if anybody else has got any other questions, I know Ray thinks he might have a couple, we can come to the Q&A section later on. So starting from the top, Rich has just asked, first of all, what is the most outstanding discovery you have made during your research?
Yes, so the most outstanding is this one that I was just talking about, the detecting the motion of our Milky Way galaxy in response to the Large Magellanic Cloud. So getting back to this idea of gravitational pull, even though you see the Large Magellanic Cloud as this relatively small thing in the sky, you actually know that it has a much larger gravitational pull, and that lets you weigh the Large Magellanic Cloud. So you can actually make measurements of how massive the Large Magellanic Cloud is. And so when I was in Edinburgh before, and when I go back, I'll be working again on the Large Magellanic Cloud. And the key point here was getting a new idea of what the mass of the Large Magellanic Cloud is and how much it's pulling the Milky Way. And then actually using the data from this satellite, again, thanks to a lot of the work in Edinburgh that's taken place, using the data from the satellite to be able to measure that tiny displacement of the Milky Way.
I think again, we're talking about expansion. Rich's next question does this analysis take account of galaxy mergers?
Galaxy mergers are happening on that billion year time scale. So I'm sort of skirted the edges a little bit. Galaxy mergers take about 1 billion years to take place. In fact, our merger with Andromeda, which will take place, but don't freak out, it's not going to take place for 4 billion years from now. But that merger will actually happen. So I sort of skirted it by stopping at 1 billion. I hit just enough time so that you see galaxies move, but not enough time that you have to really worry about mergers. But please have me back to talk about mergers. That'd be great.
That can be the next talk, as you mentioned earlier on. So
Absolutely.
actually, Rich's fourth question, so I'll skip over his third and come back to that, but his fourth question is, does your research allow you to model our collision with Andromeda? And you've already mentioned there that potentially it's 4 billion years time.
It does. I've started working on this. I had a student actually who's working at the University of Edinburgh this summer, who's if you happen to be in Edinburgh next week, he's giving a talk at the Royal Society of Edinburgh on his research that is starting to work on the merger of the Milky Way and Andromeda. So again, if you give me 2 to 3 years, I could probably have some images of what it will look like.
Sweet. I know some people are concerned about the collision with Andromeda, but I think the sun will have exploded by then. So,
yeah, nothing to worry about there.
Yeah,
but...
brilliant. I can hardly wait. Next question from Rich. What discoveries do you think your research will yield in the next few years? Obviously, I think you've discussed that already, some potential expansion beyond the billion-year timeline, but what else have you got on the pipeline?
Yeah, so I'm really interested. One of the things that I sort of glossed over, I'm really interested in how these globular clusters and dwarf galaxies. So I showed in the middle those red and blue points that are that are distant but not super distant. They evolve over time. So globular clusters, we normally think of them observationally as these knots of 1 million stars or so. We think of them as spheres or circles or something, but they actually evolve over time themselves, again, on large timescales. And what happens is they turn into these fantastically long filaments that you've probably seen. So there's images of things called stellar streams that actually trace out how they've been traveling around the galaxy. So my research in the near term is going to be focusing on how you can trace those individual paths that the globular clusters and dwarf galaxies have been following. I'm really looking forward to doing more of that.
Sweet. So that's all that we've got through on the chat. And I think Ray is now going to jump in and ask you a couple of questions live, if that's okay.
Of course.
Over to you, Ray.
Hi, Michael. Thanks so much for that talk. It was really, really interesting. I don't know if you can hear me or not.
I can hear you. Yes.
Yeah. Okay. Good. Just I had a couple of questions actually. One of which has already been you've actually answered regarding galaxy mergers. The first thing I was going to ask you was, from what I'm taking from this talk, is it true that what we can take out of this is that that although the galaxy is moving in a particular direction, that the individual components within the galaxy are all their relative movements are all different?
Yes, that's absolutely right. So you could think of, I know I'm hammering this train analogy, but you can think, you're following one path, but what's happening inside the train cars it can look like you're not moving on that particular path. And the same thing is true, like for Earth going around the sun. We don't really feel it, but we know we're going around the sun. We're going around the sun while we're going around the center of the galaxy. So it's all of these different nested motions, but happening on different timescales.
Yeah. The other Thanks, Michael. The other thing I was going to ask is about the globular clusters. Am I right in thinking that there's some evidence that globular clusters are actually sort of ancient merged galaxies?
Yeah, I mean, if you want to get into some serious research, we've got some positions to work on globular clusters, because we don't know where they came from, is the bottom line right now. One leading theory, though, is exactly what you just said, just to sort of to lay it out a little bit more explicitly. So the thought is that you take 2 dwarf galaxies, you crash them into each other, and you lose a lot of the boring stuff, so or the outskirts of it, and what's left over is this really dense knot of stars that is the nucleus of this galaxy that has dissolved, essentially. So that's one mechanism that people think globular clusters form. The other mechanism is if they're really, really ancient, like they formed when the universe formed. So globular cluster timescales would be this 14 billion year timescale. You could have one monolithic gas cloud that collapsed and just made a perfect sphere. So there's actually 2 competing theories. We don't know which one is right. I happen to be a little bit more in this is a merger camp, but that's probably something that we hope to figure out on sort of the 10-year timescale.
Thanks so much, Michael.
Thanks, Ray. We have one question
Ray.
from Meg Lee. Meg's put in a comment, just said, as a UAE alumni, I guess I so appreciate the Kit Peak shout out. I think that must be University of Arizona, if I remember
That's
correctly.
right.
Meg Lee said, will Betelgeuse explode as a supernova in our lifetime?
Boy, that's a $1 million question for sure. I think astronomers are hoping that it will, so we'll leave it at that. I mean, it would fundamentally alter Orion, of course, but having a supernova go off close by, using again quotation marks because nothing is that close to us, would be phenomenal and revolutionary for supernova research. And of course, supernova are super interesting for a huge variety of reasons. They make all of the elements that sustain life. So everything every heavy element, most of the elements in your body are made from this. So we're certainly hoping. There was a point in 2019 actually where Betelgeuse, you might have seen this, where Betelgeuse went through what they called the Great Dimming, and people thought, ooh, maybe it's time, maybe it's going to explode. But research done by actually people at University of Edinburgh, some people that are on the James Webb team now that have done some really fantastic research, helped to uncover that it was just a passing dust cloud, unfortunately, that passed in front of it. So I know, disappointing.
Disappointing, as you say, yeah. Excellent. So that, I think, is all the questions, unless anybody, in fact, my apologies, stand by. We possibly have one more. Oh, in fact, no, great talk, Mike. This is from Tim Schroeder, who's obviously our vice president. Thanks, Tim. I believe Gaia has a couple of years of life left. Are there any plans for a Gaia 2?
There are no plans for a Gaia 2 right now. And to be honest, we are full up with Gaia data right now. So Gaia's in the middle of, there's at least 5 data releases. We just finished data release 3, took place earlier this summer. There'll be 4 and 5, and there's some really fantastic stuff going. One of the things that people actually at the University of Edinburgh are interested in would be developing a new Gaia satellite that, instead of observing in the visible wavelength, so Gaia observes with the same light wavelengths that your eye does, would be to do Gaia in the infrared, in which case you would actually see not those big dust bands that you see in the Milky Way, but you'd be able to look directly to the galactic center and measure the motions of stars there. This is a big thing that's popular at the University of Edinburgh because there's huge work. They have a lot of detector expertise in building infrared detectors. As you know, one of the instruments on James Webb was actually partly built in Edinburgh as well. And so they're hoping to leverage some of that technology that they built for Gaia 2, but with the speed that things move, faster than universal scales, but that's probably a 20-year time scale to hope that that comes to fruition.
Excellent. Thank you very much. I hope I'm not stealing Stuart's thunder later on, but I was reading today about the latest James Webb imageries with exoplanets, which is fascinating. But sorry if I've stolen your thunder, Stuart. I think that is everything, unless anybody else has got some more questions. But cheers, Mike. Thanks so much for your help. And I'll hand you back to Pete.
Okay, over to you then, Rich.
Hey, Michael, that was a fascinating and amazing talk. And I particularly like how you used all these analogies and quite simple slides, which is always a benefit, that there isn't a huge amount of information that you can't quite understand. So yeah, great slides, and you communicated with them very well and communicated your point. So yeah, we all really enjoyed it. As a little thanks, we'd like to now, if I can show this, give you a whiskey tumbler to thank you for talking to us. So
that's gorgeous. Thank you.
If you bring it up with you when you come to see us, mate, we can fill it with a bit of whiskey, maybe.
Love to.
Anyway, look, thank you, Michael. That was great. And if you could let us have your address, we'll get this sent to you anyway.
Will do.
Okay, thank you very much. I'll hand over to Pete.
Yeah, that was great. Thanks, everybody. I'd say we're definitely going to get you back to talk about the barred spiral. I reckon that'll be a good talk, and maybe we can go to a different bar afterwards to get that glass filled up. How's that?
Absolutely.
Okay, well, Mike, thank you very, very much again. As I say, we will get you up one day, and brilliant talk. Fantastic. What we're going to do now is going to go for our 10-minute break, and we'll be back about 20 to 9 with Stuart in the second half with his space news, and then Mick with the Morning Sky at Night, and then a little bit of club news for you to finish off with, and we'll be finishing around about 9:30. So everyone go and grab yourself a little drink, a little cup of coffee, whatever you want to do, and we'll see you back in about 10 minutes. Take care, everyone. Okay, everybody, welcome back to the second half of the Sigma meeting for September 2022. Just before we go over to Stuart with the space news, I've got a couple of photos to show you from Ray, who sent them in. Wonderful photos. You may have seen them in the newsletter. Ray, if you're there, would you like to come and speak about your photos and tell us how you actually took them? If so, just put your hand up and I will let you talk. I shall put you on to let you talk anyway. How does that sound? Just give me one moment here. Should have organized this previously, really, but there we go. That's Sigma. Things happen. Where do I go up here? Panelists. Right, he's put his hand up. So Ray's going to say it's all about his photographs that's coming up. When you want me to move on to the next, picture, just let me know, Ray. Okay? Are you should be able to speak?
Yeah. Yeah, you kind of caught me in the hop here.
Yeah, it was just a thought I had just when I come back to the seat.
Yeah.
You know?
Well, I'll try my best.
Okay, so here we go. Here's the first one.
So this is the Rosette Nebula. It's also known as Caldwell 49. It's Patrick Moore's catalogue. It's in Monosaurus, and it's associated with the cluster you can see at the center here, which is NGC 2244. It's about 50,000 light years away, and it's approximately 130 light years in diameter. And all these dark clouds are known as Bloch globules, I beg your pardon. And so the dark areas that are evident in this picture are actually active, or thought to be active sites of star formation. Now, I used to do a lot of narrowband imaging, you know, using a monochrome camera with hydrogen alpha, oxygen 3, and S sulfur 2 filters. But I just found, because where I used to live in particular, and the sort of vagaries of the climate in the UK generally, I just wasn't getting enough integration time, and I was getting more and more frustrated. So I actually started going over to one-shot color cameras and using this new thing that came out, an L-Extreme dual-band narrowband filter, which was what this was taken with. It was taken through a Skywatcher 120 Esprit refractor with a 2600 MC Pro one-shot color camera, but using this as I say, this L-Extreme filter, which has a very, very good narrowband. It only allows, or selectively allows hydrogen alpha and oxygen 3 through. And with a bit of clever processing, well, for me at least, in PixInsight, you can actually produce something like this picture here, which is, to me, is not far off a true narrowband image. Dare I say it. I've got a picture of this that I took with the narrowband, but I'm not put it up. But I was really quite actually pleased that, you know, the results I got from this color camera compared to the true narrowband stuff. It's not far off it at all. So yeah, it's a popular winter night image. Now, the next one, sorry, this is a supernova remnant. Samiz 147. It's huge. It's about 3 degrees across, and it's the remains of a supernova that blew up 40,000 years ago. It's about 3,000 light years away. The problem with it is it's incredibly faint. It's because it's spread over a large area of the sky. It's very, very faint. And it took me 3 nights of imaging to actually get this. I got a total integration over 3 nights. It shows you how bad the weather is. It's 275 minutes. But I used a Sharp Star 61 EDPH2 with a 0.8 reduction on it. And again, using this one-shot color camera, and again, yeah, with the L-Extreme dual narrowband print. And I was actually very pleased with this, actually, although it's probably not the most spectacular photograph of this object, but I was actually quite pleased given how faint it was and how little time I had imaging it. So I want to move on to the next one. Sorry, I didn't take up your time. Yeah, it's a Veil Nebula. You know, at this time of year, it's very high in the sky. And again, using the Sharp Star 61 EDPH with a reducer, and again, using this L-Extreme dual band narrow filter, 150 minutes. But what was good about this combination, because the camera has a AP3 chip in it, you pretty much got the whole thing. Most people are probably used to just seeing parts of this in images, but I managed to get the whole thing in.
I must say, Ray, that is actually stunning. So I know just how faint the Veil Nebula is to actually try and see.
Yeah, but you know, but that combination of the telescope and the camera and with L-Extreme, I managed to get the whole thing. And as I say, normally most people with the kit you get, you're only going to. People tend to image the individual components of it, but that particular thing, we managed to get the whole thing. Sorry, moving on. Yeah, I like this. It's not the most spectacular photograph, I have to say, but it's actually what you're looking at, to me, sort of blows my mind, and it kind of goes into Michael's talk this evening. And this is what's called the Leo galaxy. It's in the constellation of Leo. Obviously, it's about 330 light years distance. And in this photograph, depending on on which paper you read and which source of material you read, that there's about 100 galaxies in this photograph. Pretty much all of the points white are actually galaxies. And it was taken again with the SPE 120. There's a fair magnification on this, and again with the 26 MC Pro, but without any filter. This is unfiltered. It's just a simple infrared cut filter that was on here, and again managed to do it with 126 minutes total integration time, and the colors have come out quite well. I think you can see definite galaxy structures and all these things, and it's part of the general supercluster in there, of which you've got the things like the Markarian chain as well, and if I forget the other ones offhand, but it's that whole region of the sky in Leo and Virgo is awash with this kind of imaging. But it's as I say, it's not perhaps particularly exciting to look at, but for me, it's what each of these things represent in the distance they all are.
Because that's the chain there, isn't it? I believe. Is that
No,
right?
this is not the Markarian chain. Is not
Oh, no.
but Markarian chain is part of this whole
part of it.
superstructure. This is only one little part of the entire structure. It goes right across the sky, really. It's part of the. Michael will probably explain it a lot better than I can.
No, after your stunning images, Ray, and please
Right,
keep.
thanks very much.
Thank you very much. Okay,
That's
right. We will now
cheers.
move on then to Stuart with your space news. I will get rid of this. Stuart, are you there? Hello, Stuart.
Yeah, here.
Gotcha.
Just selecting. Okay.
Okay, we've got you.
Right. Welcome
Over
to
to you.
Space News. Got things on my screen for some unknown reason. There we go. Right. Space News, September 2022. What I've done, I selected a few items which aren't sort of major items. A lot of the major items now appear on the news, so you probably get lots of information about them from the news broadcasts. So I've selected some of the lower items, which I found quite interesting. However, this one I just stuck in at the beginning was the Artemis 1, which I was hoping to put in a shot of it being launched. But apparently that's supposedly going to happen tomorrow. So Artemis 1, just a couple of things on Artemis 1 is the unmanned version, which will do an orbit and come back. Artemis 2, which is supposed to go off in 2024, is going to have a crew of 4 and do a similar thing. Then Artemis 3 will launch and planned to land on the moon, and they've now selected the sites that, or supposed sites that it's going to land on. So things are actually moving ahead, which is quite good. Right. Oops, my screen has just stopped moving. There we go. Right. On the 24th of July, China launched one of their Long March rockets with the new module for the Tiangong space station, the Wentian model. The rocket reached its orbit along with its payload and stayed up until atmospheric drag brought it down in an unpredictable and uncontrollable fashion, which NASA made some rather scathing remarks about. However, in the end, they said it entered the 25-ton course stage of the Long March, entered Earth's atmosphere over the Indian Ocean on the 30th of July. One observer appeared to capture the rocket's breakup from Kuching in the Malaysian state of Sarawak, and he put it on Twitter. And this is where you see the high-level breakup. It implies it was in the atmosphere at that time. Any debris would land hundreds of kilometers further along the track near Cebu, Bintulu, or even Brunei. Eventually, Chinese officials came up and said it re-entered at 119 degrees east longitude and 9.1 degrees north latitude. And the location is over open ocean, just off the coast of Palawan Island, which is part of the Philippines. Most of the debris burned up, they claimed. Now, this was the third uncontrolled fall for a Long March 5B core stage. To date, about 10 days after the rocket's debut launch in May 2020, pieces of the rocket body rained back to Earth over West Africa. Some of them apparently hitting the ground in the Ivory Coast. And the rocket's second flight in April 2021 launched the Tiani, the core module of the Tiangong space station. That Long March 5B body re-entered Earth's atmosphere over the Arabian Peninsula about a week after liftoff, dumping debris over the Indian Ocean. And there's a chance now that it's going to happen again when they launch the next part of the Tiangong module in the autumn later this year. To come on to the Tiangong space station, China hopes that it will replace the International Space Station, which is due to be decommissioned in 2031. However, Chinese astronauts currently are excluded from the ISS because the US law bans the space agency, NASA, from sharing any data with the Chinese. So here we've got their space station. At the moment, the Wentian, which is the one that's just launched, is on the left of the space station. Mengtian is the next one to be launched, which is on the right. And Tiani is the main body or core of the space station there. Now, China has produced an animation of the space station, which I'll try and show you. And I'm going to move it along because to there. And this is China's plan for program for the future. 2022 finish the construction of the Tiangong space station. 2025 collect near Earth asteroid samples. Launch Mars sample return mission. 2030 send unmanned probe to Jupiter. 2030 land astronauts on the moon. 2035 develop reusable carrier rockets. I would have thought they'd have done that earlier on the basis they're dropping from the atmosphere. 2040 build nuclear powered space shuttle. and 2045 become a leading space power. So that's their program for the future. Now, India had an interesting start. India's new small satellite launch vehicle launched for the first time with 2 payloads on the 7th of August. It failed to deliver its satellite payloads into the intended orbit due to a sensor issue, and they were deployed in the wrong orbit. Instead of placing the satellites in a circular orbit 221 miles above Earth, the rocket left them in an elliptical orbit that ranged from 221 miles to as close as 47 miles. That orbit was not stable. It is believed that the satellites have already come down and hence they are not usable. The rocket's 3 fuel stages performed well, but its 4th and final stage, a liquid-fueled velocity trim module, hit a snag. Indian Space Research Organisation official reported the loss of data from the rocket and just over 5 hours after liftoff, and announced the mission had failed. The sensor failure was not detected. They say a sensor failure was not detected in time to switch to a solvered action, which caused the orbit issue, and they're now investigating it. Now, the main payload on the test mission was an Earth Observance Satellite 02, and this microsat series satellite offers advanced optical remote sensing operating in infrared band with high spatial resolution. The second satellite was an 18-pound CubeSat called ASADSat, and this small spacecraft was loaded with 75 different payloads, which were built by, believe it or not, female students across India to perform a variety of femto experiments. And they included a UHF-VHF transponder working in ham radio frequency to enable voice and data transmission for amateur radio operators, a solid-state PIN diode-based radiation counter to measure the ionizing radiation in its orbit, a long-range transponder, and a selfie camera. So interesting, a second satellite. NASA's ShadowCam. NASA selected Korea Pathfinder Lunar Orbiter to launch their ShadowCam. On the 4th of August, NASA's ShadowCam, developed by Arizona State University and Malin Space Science Systems, headed to the moon aboard the Korean Aerospace Research Institute's Pathfinder Lunar Orbiter. The orbiter launched on a SpaceX Falcon, as you can see there, from Cape Canaveral. And over the next 4.5 months, it will use a fuel-saving Korean ballistic trajectory, 62-mile lunar polar orbit, where upon arrival it will begin operations on a planned 11-month mission. They called it, the orbiter is known as Danurai after a public naming contest resulted in a name combining the Korean word for moon, Dal, and enjoy, Nuri. And ShadowCam is one of the 6 instruments on board the spacecraft. And we'll see what it comprises of. That's the lunar orbit module. And ShadowCam is a hypersensitive optical camera which will collect images of permanently shadowed regions near the moon's poles. This will allow ShadowCam to map the reflectance of these regions to search for evidence of ice deposits, observe seasonal changes, and measure the terrain inside the craters. It's based on previous images like those found on the Lunar Reconnaissance Orbiter, but is several hundred times more light sensitive to allow for capturing details within the permanently shadowed regions. In addition to ShadowCam, NASA is also communications and navigation support to the Korean science organization to support the team, and they've provided 9 NASA-funded scientists. And that's the ShadowCam unit itself. And there's a further one of the ShadowCam, which is technical drawing, the shadow cam. And that's some of the makeup of it. Starship Super Heavy booster test is carried on from last month's space news. It was still having problems. Did a static fire test of the booster 7, which is the rocket part of it, on the 9th of August. And also on the 11th of August, it carried out static fire tests on the booster 7, which was attached to its base using one Raptor engine. On both times, they used different engines. And on the 11th of August, the booster returned to its processing bay, and the remaining 13 Raptor engines installed. It's hoped that it will now progress eventually to all engines being tested. But I gather, I haven't got further detail, but on the 31st of August, he did a test with 3 engines, but apparently only 2 of them fired. But I haven't seen any reports of that. And it'll eventually continue till it does 33 engines. And that's hopefully Starship program is going to merge with the Artemis program because NASA is going to use it for transporting astronauts to the moon. And this is a test. They did this in reverse order. Got the earlier. They tested one of the engines, and then they did the Raptor tests. Further Raptor tests. Do a slow motion one now of that. And finally, NASA's DART mission. And the idea is it will test asteroid defense techniques by conducting an asteroid redirection test. Though the threat from asteroid impact is small, according to the Planetary Society, is a threat nonetheless, and something we should be prepared for. We only need to look at past impact events, such as the massive asteroid impact that is credited with the extinction of the dinosaurs 65 million years ago, which was mentioned in the earlier presentation, to see the catastrophic effects an impact can have on life on Earth. Early detection of near-Earth asteroids is the first step to planetary defense. Approximately 30 new discoveries of near-Earth asteroids are made each week. And at the start of 2019, there were more than 19,000 discovered near-Earth asteroids, according to NASA. And DART is the first mission to test an asteroid deflection technique. NASA launched its Double Asteroid Redirection Test Mission, or DART for short, on the 23rd of November 2021, atop a SpaceX Falcon 9 rocket from the Space Launch Complex 4 at the Air Force Base in California. Its target is the binary asteroid system, Didymos, which means twin in Greek. The system consists of a near-Earth asteroid measuring 0.48 miles across, and its moonlet, Dimorphos, measuring 525 feet across. And it's scheduled to arrive on the 26th of September. So it's something to look out for in this coming month if it gets mentioned on the news. Here's an animation of what it's planned to do. NASA's Double Asteroid Redirection Test Mission, or DART for short, launched on the 23rd of November and is planned to arrive, as we mentioned, on target on the 26th of September. It will deliberately impact Dimorphos at a speed of 4.1 miles per second, and the impact should cause the moonlet's orbital speed to change by a fraction of a percent. Slight shift should be enough to change its orbital period by several minutes. The change in Dimorphos orbit around Didymos will be observed and measured by telescopes on Earth to see whether the mission has been a success. And that's again showing it there. Though that the pair are not a threat to Earth, they are perfect candidates for the DART mission, as Dimorphos is around the same size as an asteroid that could pose the most likely threat to Earth if one were on a collision course with the planet, according to NASA. Their orbit around the Sun is close enough to Earth for ground-based telescopes to observe and measure any differences after the collision. About 10 days ahead of impact, DART will release a small CubeSat called Light Italian CubeSat for imaging of asteroids, which you can see just there to the right of the DART. It's built by the Italian Space Agency, and the CubeSat will watch the impact in real time and send Earth images at the brand new crater. The European Space Agency will launch a follow-up survey mission in 2024 called Hera. That spacecraft will study the two asteroids in greater detail, including checking up on the impact crater and measuring the physical structure and chemical composition of the double asteroids. Okay, so that is the end of space news. Thank you.
Thank you very much, Stuart. Wonderful presentation again. As I say, we're going to give you a little bit of a break now, because we all know how difficult it is to put these presentations together, and I think you need a rest. But fear not, everybody.
Right.
Stuart is still going to put a little bit together and put it into the newsletter every month, so everything is not lost. Right, so we will now move on to Mick, and we'll go over to what's happening in the Moray sky tonight.
Thanks, Pete. I'll just share the screen here. Okay. Got that okay?
Yep, that's fine.
Right. Good evening all. Welcome to Sigma's September 2022 edition of the Moray Sky at Night. As usual, I'll start with the moon and the planets. So our inner planet Mercury is close to the sun this month, and it reaches inferior conjunction on the 23rd. Venus is also close to the sun, but it may be glimpsed in the morning twilight later in the month. Mars is moving eastwards in Taurus, brightening from a magnitude -0.1 to -0.6 over the month, reaching a good altitude at midnight. Jupiter reaches opposition on the 26th, its closest point to the Earth this year at 591 million kilometres. It'll be at a spectacular magnitude of -2.9 and in a subdued star field in Pisces, so plenty of details should be on offer. The transit phenomena of the Galilean moons are always interesting, and on the night before opposition, so that's the evening of the 25th, Io transits mid-evening and occults its own shadow. So that's something that could be worth looking out for. Saturn is in Capricornus at a magnitude of +0.4 to 0.5. Uranus is in Aries at a magnitude of 5.8. And that's going to be occulted by a waning gibbous moon on the evening of the 14th, which I'll show shortly when I go through Stellarium. Neptune is in Aquarius at a magnitude of 7.8. And that beats Jupiter to opposition by 10 days on the 16th of September, when it will be at its nearest point to Earth at 4,325 million kilometres. Okay, looking on, excuse me, what the moon's travels through the month. 6th, 7th, on the 8th, it's going to be passing by Saturn, then close to Jupiter on the 11th. And as I mentioned on the 14th, what I'm going to do now is go to a little look here. Oh, what's happening? Constellarium. Right, I've gone too far. So it's going to occult Uranus. There's a good and a bad side to this. The bad side first is it's going to be passing behind the brighter side, the brighter limb of the moon. So that'll be quite difficult to see because the moon is really bright there. But if we go to an hour later, it's going to reappear from behind the moon round about 29 minutes past 11. So if it's a cloudless night, I think I might have a go at that. Although I wouldn't be up here actually. Never mind. Anyway, so that's something you can look out for. Now this this event is actually very rare. The last time that an occultation of Uranus was visible from the British Isles was 1955. But even more amazingly, there are 2 occultations of Uranus this year, the next one being on the 5th of December. So continuing with the moon's travels, it's going to be passing between the Pleiades and Aldebaran on the 15th, close to Mars on the 16th, then continuing through the month. I'll take the time up. Let's get the twins up. Passing by Pollux and Castor. 23rd of September is the autumnal equinox for us up here in the northern hemisphere. And that's the time the sun crosses the plane of the equator as it heads south, marking the start of autumn and when nights become longer than days. On 24th, well, I have to keep going, just before dawn on the 25th, the moon is going to be right next to Venus. So that's something you might want to look out for if you're an early bird. But be very careful, obviously, if you're looking in that direction because you're going to have the sun rising. Be very aware of the time the sun's rising. Certainly don't point any cameras, telescopes, or anything towards the sun, or it will make you blind if you catch that in your optics. On to meteors. If I go to the back to the night, oh, what's happened here? Williams at a wibble. Yeah. Yeah, it's going to be. Okay, after the major Perseid meteor shower in August, there's very little shower activity in September. There is one minor but very extended shower known as Alpha Aurigates. The radiant is going to be around here, so if you look anywhere above to try and catch some. These were at their maximum around the 31st of August, 1st of September, but activity might extend into October. It's a weak shower as a rule, but occasional outbursts have been recorded. As a slight compensation though, the number of sporadic meteors in September far outnumbers the rates of any other times during the year. So that's the planets. Let's go and have a look at some deep space objects. And I want to be where are those meteors? Let's get my field of view right so you can see everything I'm talking about. Okay, so the summer triangle is now high in the southwest, made up of 3 first magnitude stars, Altair and Aquila, Deneb and Cygnus, and Vega and Lyra. Vega Alpha Lyrae is a brilliant blue-white treasure. Lyra is a small but perfectly formed constellation, which contains the famous Ring Nebula, Messier 57, down here. And it also contains within its boundaries the often overlooked globular cluster M56. And going further up, if we go back to Lyra, sorry, Vega and Lyra, and I'll just zoom in again. We also have what's known as the double-double. So just here, you see this blob. We have Epsilon 1 Vega, Lyra, sorry, Vega in the head. Yeah, so this wide pair of stars. Within each of these components, there's another closer double. So it's a good test for small telescopes. The wide pair are easily separated using a pair of binoculars, as the two binaries are 208 arc seconds apart. Epsilon 1 are stars of magnitude 4.7 and 6.2. If Solarium doesn't zoom in far enough to split them, but worth a go, I think. And Epsilon 2 on a similar vein has two stars, a magnitude of 5.1 and 5.5. Zoom back out. With some of that. Back down to the south. So rising high in the southeast this month is Pegasus. Near the Great Square of Pegasus. I'll put some names up for you. You see them. That makes up the body of the flying horse. This horse is actually upside down as viewed from our perspective. And along with Andromeda here, which is also well clear of the horizon, so ideal situated for viewing M31, our closest large galaxy, Andromeda, M31, which I mentioned earlier on. And some 15 degrees below this, so you come straight down about the same distance as that is through Mirach, round about here. I can never get the information up. If it come up, it'd been our first today. One of these, there we go. Some information for you. The Triangulum galaxy, sorry, M33. Now, lower in the sky, you can see the Pleiades are starting to come up now. That's a good indicator that autumn is almost upon us. And these are certainly worth having a look at through a pair of binoculars. Really sparkle like diamonds, absolutely amazing to see. Looking to the south, we have Aquarius, which contains the second object on Charles Messier's list, M2. About here somewhere, there we go. This is a fine globular cluster with a magnitude of 6.3. Coming back out and going back around to the north, we have let me come out a bit in a bit. Yeah, we have Ursa Major immediately below the pole. That has a popular pair of galaxies, M81, M82. Here somewhere. I'll just zoom in a bit. There we go. Should be Bode's Galaxy one. Yep. There we have M81, Bode's Galaxy, and just above it we have M82, Cigar Galaxy. So just across from Ursa Major to the northeast here, we can see Auriga, main body of Auriga's come up with Capella. Capella's going to be riding high in the sky, right into the depths of winter. I mentioned near the pole, if we come back to Ursa Major, for those of you who aren't aware of how to find the pole star, Polaris. So Stellarium's drawn the whole constellation on here, but we often just find the asterism in the sky, which is part of the constellation, the Big Dipper. So I think it's like a chip pan. So if you take these two stars in the bowl of the chip pan, follow them straight up, almost directly overhead, the next brightest star you're going to come across is Polaris, Pole Star, the North Star, obviously part of Ursa Minor, the little bear. And we have Draco snaking around here on Cepheus. And inside Cepheus, we have a variety of open clusters. The brightest being NGC 7160. And also accommodates the well-known Elephant Chunk Nebula within its boundaries, which is just here. I won't auto zoom in on this because it was in too far. That's the Elephant Chunk Nebula. Okay. And finally, for September, I'd like to put a little challenge for you to find. Right, where am I? Right. So what we're going to look for this month's an easy one of Pete's favourites. I'm sure you'll agree. It's M27, the Dumbbell Nebula. So to find it, find Albireo and Cygnus. So it just happened to be here. There's Deneb and Cygnus. The opposite end, this one, is Albireo. Just next to it, we have Vulpecula, followed by Sagittare. If we head down to Sagittare and get the head star in Sagittare, and then we're looking for 13 Vulpeculae, which is this star here, and round about halfway between the two, so about there, we have the Dumbbell Nebula. Fantastic to see. Looks more like a apple core to me. Anyway, known as a Dumbbell Nebula. So that's all from me for this month. I shall hand you back to Pete.
Thank you very much, Mick. That's going to give us plenty to get our teeth back into now the Dark Knights are arriving back, and say some good objects there. If you're novice or even if you're experienced, you can get your talented skills again, because I know I lose them over the summer to anybody else. Okay, we'll finish off with a little bit of club news. I've already mentioned the BA meeting that's happening next week. So starting on Friday, September the 9th, an evening, and going through to Saturday, September the 10th, which is an all-day session. Tickets for that event, are available on the BA website. You do get a 20% discount for a Sigma member. Information about that can be found in the newsletter to put the code in for your discount if you haven't bought your ticket already. If you have bought your ticket already and didn't know about the discount, tough. To say the BA link is actually britastro.org/events/Elgin-2022. Okay, just let you know about that one. Obviously, it's open to everybody, so any visitors here who aren't members of any of the clubs, get yourself a ticket and come along and meet us there. Okay. I want to thank all the members who've put forward, want to help out at the event, because we are going to need just a little bit of help to, show if we get members of the public where they're going and this, that, and the other. And also the main thing that Hazel, who's the organizer from the BA, said is for doing a sweep at the end of the actual events to make sure no one's left anything behind. But if you want to help out on the Friday, if you can be at the HCI about 6:30, that'd be great. I say the doors open at 7 for a start at 7:30, and on the Saturday morning we'll be there about 9:30. Say once again, doors open at 10 for 10:30 start, and that goes through to about 6 o'clock at night. Okay, there is also arrangements to take them down to Glen Grant Distillery in Rothes. They always try and do something local on the Sunday before they all head back down south. So we suggested going to the Glen Grant Distillery there. that's all been organized at the moment, but we might need a couple of people, if possible, to ferry the BA members back and forth. There's only going to be about 6 or 7 of them, so we can probably do it in 2 cars, but if we've got an extra car there, it will always be helpful. So that, if you can help with that one, let me know on a Saturday, and then we can sort of, so let you know the time rather than go through it all tonight. But hopefully we'll see you. Well, I know I'm going to see a few of you there next Friday and Saturday, and let's push forward and prove to the BAAs. They were very reluctant to do a talk this far north because it's costing them a fortune, they said, to come this far north. So hopefully we can get together and prove to them, yeah, we have got a thriving astronomical sort of society, and going on up here, and we can prove to them you can come back perhaps one day. So the talks that they're doing is a fantastic array of talks, all on the website, BA website, or our website, and I say tickets available there as well. Future meeting plans. It's been decided that Sigma will hold online Zoom meetings during the winter months, so it's January, February, March. Okay. Physical meetings for the rest of the year. There may be the odd one thrown in that may not be, like tonight when our speaker is stuck somewhere else around the world. The only exception to this is going to be November, when we got Neil Reed coming in from USA. Okay, so the November, we'll make a note of that, is going to be Zoom only again. Okay, next month we are down at Lambride, but November is going to be Zoom only. The reason we sort of done this is to say we've trying to please everybody, which I know is actually impossible. Some people want to just stay on Zoom at the moment. Some people want to go back to physical meetings. So if we do at least 3 a year, then hopefully we're keeping most people happy there. Okay. As I say, we will not be, we've been decided we will not be at the moment, possibly not ever, streaming the meetings out of the hall. Okay, the technical difficulties behind this is just too much. There's enough for the committee to set up at the meetings to do with anyway, just to do a physical meeting, and to do anything else would actually mean you need another group of about 5 people setting up the Zoom side of it, and the acoustics and everything is a little bit of a problem. We're going to see what we can do, but at the minute, there's no plans for that at all. Apart from we'll try and record it or get it to Chris, because obviously Chris is down in Lincoln. He does all the arranging of the speakers, and be a bit unfair if he can't actually join in. But as it goes to going out to the members of the public or members of the clubs, it's not going to happen at the moment. Social media. I said, I mentioned this last time I was there, that obviously we need a big social media presence now. Everything's going that way. If you think you could help out by just all we do is, if you're on Facebook or any of the other sort of social media, Twitter, Instagram, like that, if you know how to use it, we can give you access to the accounts. And it's just a case of putting up posts now and again, keeping the events up and live, just to keep us ticking over. Anyone who can do that is more than welcome. You don't have to come on the committee to do it. We'll just give you the links and away you go. Okay. Flickr's all taken care of. Helen looks after that. Well done, Helen, for that. I'm going to say, but the other side of it just needs constant input. Well, not constant input, but regular input. Let's put it that way. Outreach. Outreach is really taken off again now. The Tom and Tell and Glenlivet Star Party on the 23rd, 24th, and 25th of September. I'm doing a talk on the Saturday afternoon. But not decide which one yet. I can see what the speaker's doing a talk about before I decide. Some of it is free, some of it is ticketed, but if you go onto their website, you will actually be able to see what what you need to book for. I think anyone can turn up. Once again, it'd be great to see a few Sigma members up there helping them out. Sam really does help out Sigma a lot. He's one of the organisers on the committee up there, and if we can show a bit of presence up there, it'd be great. Fantastic. So we'll put a link. I think a link may already be up on the Sigma website. If it's not, I'll get Helen to put one up. Okay. Another one just been brought up is the Kabrak. They've asked me to, ask Sigma to do a talk. I've put my name forward. Obviously, it's not going to be me. If anyone else wants to come forward sometime and say, well, I'll do it, just let me know when we can. We'll come along with you, of course, obviously. But if you want to do a talk for them, let us know, and we'll get you booked in. So that's the Kabrak. I think that's the 1st of October. And just yesterday, I was contacted by Mostoglock Cubs or Scouts. I say it's so recent I haven't had time to read it. I think it's the Scouts, and they've asked us to do something for them as well. So the outreach is starting to pick up a bit. So hopefully now we can start moving on with that a bit more. Observing nights, we're not going to try and do the observing nights like we did before, where we're booking Fridays and Saturdays, because it just hasn't worked with the weather. What we're going to do is the morning astro meet. So keep an eye on your on your email inbox if the skies are clear. If a couple of us say, right, we'll go for it, we're going to put an email out saying, right, here we go, we're going to meet here tonight, just for a couple of hours, whatever, and we'll get observing. We'll try and do one very soon. I'm just thinking about that one that Mick had just brought up. I didn't even know about it. On the 14th. Maybe we'll try and do something for the occultation of the moon and Uranus. That'd be quite interesting if we can do that, weather permitting. But as I say, we're going to do more of the more astro meets. It's going to be easier to organize, and it's going to be spur of the moment sorts of things. But we will get out there looking up in the sky sooner or later, if the weather gods are kind to us. The newsletter, you will all receive your new format newsletter. Well, say all of you. I didn't get mine for some reason, but there we go. I'm only the chairman on it, but no, it is an email issue. Don't worry about it. And I hope you all like it. And you will see there's a little thing called Members Corner. This is your chance to put something into the newsletter. If there's something you've been doing, or some images you've been taking, or anything you've been doing, and you want to let the rest of the club know, just write something down. It hasn't got to be, a massive a massive input. It could be a few, sort of few paragraphs, a couple of pictures, anything like that. Send it over to Rick or to Rich or Helen, and they'll get it popped in there for you. Okay. Put a big thank you out to Rich and Helen and Tim and all the others who have actually worked hard to get this newsletter in the format that it is. It's saved me a heck of a lot of work, and thank you very much for doing that. But thank you very much for doing the newsletter as it is. I'm sure you're all enjoying the new format of it. Don't forget to invite a friend to Sigma. As I say, we're back at Lambride, so if you've got any friends who want to come along, just grab them by the scruff of the neck and drag them up. Okay. And I say, we're always looking for new members, always, because the more members we get, the easier it is to keep the membership fees down, if you know what I mean. Just to say, their first meeting is always free, as is our remit to try before you buy. So just bring them along and see how they get on. Or if they want to come to the Zoom meetings, let us know, and we can, or even just share your link with them. That's the way to do it. Okay. Don't forget, if you ever have anything from me, just ping me an email or pick up the phone if there's anything you think we can be doing better or we're not doing right. Or if there's anything you want to ask us, just pick up the phone and let me know. So with that, it just leaves me to thank everyone for tonight. Obviously, Mike, I know he's gone now because obviously Paris is 1 hour ahead of us, so it's now 25 to 11 over there. But for his wonderful, superb talk, it was absolutely brilliant. I've loved it, and we will get him back to have that talk, I think, on the Barred Spiral Galaxies. Ray, your wonderful images. Keep them coming. Do please keep them coming. I think Alan Tuff has got a little bit of a competition coming up. Stuart, for your space news. As I say, we're going to miss it for the next few months. We'll be back in April, I think. We'll do it again in April. As I say, but there will be little inputs going into the newsletter for the space news. Mick, great first morning sky at night. I say some fantastic objects there to get our teeth back into it. And Rich for being the co-host there. As I say, you can't do it without having a couple of co-hosts in the background. Luckily, touch wood, I haven't dropped out tonight. It does happen from time to time, and it's always good to know there's someone there to take over if it happens, and also helping with everyone helping with the organisation and getting this to go in together. But also, thank you lot for coming along. It's great to see so many of you here. I think we had about sort of 30 odd people, which is quite good for a Zoom meeting. And with that, just keep looking up. Nights are getting dark. The stars are coming out. And we'll get observing again one night. Okay, so take care, everybody, and good night from me.